In this video, we're looking at sampling distributions and biased and unbiased estimators. So there's a general idea in statistics that we're interested in studying something about the population. So that might be, for example, the population mean. So say we've got some sort of medical study and we want to know how the change in somebody's blood sugar is affected by a certain drug. So we're going to look at an average, right, since we know that might vary by person, and we'd like to know, how that changes for all people, but typically we can't actually study the entire population of people. So what we end up finding instead is actually the mean of the sample. And we've looked at this before, right? We take a sample of people, compute a mean of whatever kind of data we're looking at, and we want to compare that to the population mean. Now these don't have to be means. We could also be looking at, say, the percentage of people with a particular opinion. That would be a proportion. We could look at standard deviation. We could look at medians. We could look at all different kinds of things. But the mean is a good one to kind of keep in your mind when you're thinking about this. So a simple example, say we want to know what the average height of American women is. Well, we're probably not going to be able to actually measure the height of every single woman in America because that's just impractical. So what we do is we take a sample. Now, the mean height of the sample might not be exactly the same as the mean height of the whole population, because we might have happened to get some shorter people or happened to get some taller people. But if we repeat taking samples, and in this context we're assuming that all the samples are the same size, typically size n, that they're all simple random samples, and that we sample with replacement. So if we were taking samples over and over and over, we'll allow the possibility that we measure the same people twice rather than taking the people out of the population each time, so that these are all independent. So when we repeat samples, we're going to get some means that are maybe much less than the population mean, some that are much higher. Most should be right around the same size as the population mean. And in fact, these means are normally distributed, which we'll see in the next video. But on average, they're going to be close to the population mean, but spread out a little bit on each side. So because these sample means are sort of distributed around our population mean, this sort of unknown mean of the whole population, mean is called an unbiased estimator, meaning it targets the population parameter. So if we take the mean of a sample, it's going to be close to the mean of the population. Now, because the sample is randomly chosen, we never really know how close we are to the population, but if we were able to sample over and over, we would get an idea of where the population mean actually lies. So a big part of this section is understanding the difference between an unbiased estimator that actually does target the population value. So this is true of means that we just talked about. This is also true of variance. So if you look at the variance of various samples, that will target the variance of the whole population. Remember, we use that sigma and the s for standard deviation. The squared means that we're talking about variance here, not standard deviation. And then the third common unbiased estimator is a proportion, and you could think of this as a fraction or a percentage. So maybe you're doing a poll to find out what percentage of voters are going to vote for a certain candidate. Again here, your sample poll should target the population poll. So again, that doesn't mean that they're the same, but if we took samples over and over and over with replacement, we'd get values that are sort of centered around the population value. Now, not all statistics are actually unbiased estimators, and this section has three key ones that are not. So these are biased estimators, meaning that they do not target the population parameter. So if you did many samples and measured the median each time, the average of those samples would not necessarily be the median of the population. Same thing with range. We'll look at an example of that in just a second. And same with standard deviation. So standard deviation is a biased estimator, meaning it isn't estimating our population in the way we might like it to. However, in this previous list here, we did say that the variance is unbiased. So if you wanted to look at standard deviation, what you do is use the variance instead, and then we can always just do a square root. Now there is a note in the book that standard deviation is really, it's pretty close to being unbiased, so we do sometimes see this, the standard deviation of a sample compared to the population. But again, really here, if we were trying to get that population parameter, we would want to be using variance rather than standard deviation. So we can verify this phenomenon by looking at very small populations. So imagine we have a population with only 3 values, 4, 5, and 9. Maybe these are, ages of children or something like that. Now this isn't a particularly interesting population, so we're really only doing this to get an idea of what's going on here. So since this population is so small, we of course can compute the mean of the whole population, right? There's only 3 values. The mean here would be 6. And I'm also going to look at the range. So the range of this population is 5, right? The difference between 9 and 4. And again, because this population is so small, we can actually make a list of all the possible samples, in this case of size n equals 2. Right, so the size here is important. Now remember, this is sampling with replacement, which means we can get repeated values. Right, you'll see there's a 4 and a 4, there's also a 5 and a 5, and a 9 and a 9. And all the other possible combinations of picking 2 numbers from this very small group of 3. So again, in practice, our samples are not going to be this small, our populations are not this small, but we're doing this to keep this a manageable size. Right? Even with only 3 values, we still end up with a total of 8 possible samples to check. So what I want to look at is each of these little samples, I'm going to compute the mean and also the range, right? We want to look at both of these and then compare them to the population. So I'll go through each one, right? Some of these are really easy. If you have a 4 and a 4, then the mean is 4. The range would be 0. 4 and a 5, our mean would be 4.5. Our range would be 1. And so on. So I just want to keep going through here and compute the mean and the range for all of these possible samples. Okay, so you'll see that with all of these samples, we're getting different means and different ranges. Now, if these statistics were unbiased, that means that if we look at all of these means all together, now some are higher and some are lower, but if we actually took the average of all these possible means, what we should see here is the same as the population mean. So let's check, right? If we add all of these up and divide by 8 by the number of samples, we end up with 6, which in fact was the same as the mean of this whole population. So this is what we would expect, right? Mean is an unbiased estimator. But if we do the same thing for the range, take the average of all of these ranges, in this case it comes out to 2.2 repeating. And this is not the same as the range of the whole population, right? In fact, it's quite a bit lower. This is a biased estimator. So this is just an illustration that shows us that if you take mean over and over of samples, the average of those means should be somewhere around the population average. Now, it wouldn't be exactly the population average unless we actually had all of the samples, but if we get a nice good random sampling, it should be pretty close. However, if we sampled the range over and over, we should not expect those to average out to be the population. In fact, in general, the average range will be less than the population. So that's our unbiased estimator. All right, so here's a question for you to answer. See if you're understanding this idea of biased versus unbiased estimators. And I'll see you in the next video.